if you're just coming in, this session and the next one are both an introduction to modern C++ techniques. As an introduction, we're going to be able to cover some items, some more in depth than others. Because it's my presentation, I'm going to cover the ones I like more. But you're not going to walk away as some modern C++ ninja, but hopefully you have the skills that you need and some questions that you go out and start discovering on your own. So let's see. The first thing, I guess, my name's Michael Case. If we haven't met yet, I'm with Kiara Consulting. There've been a couple questions now why our logo is a lambda, and it actually has nothing to do with my lambda talk. Kiara is a Latin word that means to set in motion or to conjure, and lambda for other engineering things is used as periods of motion, and so that's where it came from. All right, let's go ahead and get started here. If you have a laptop and a compiler, you'll want to get that going. We're going to need them. The alternate title to this presentation is, this is the session I wish I had the first time I came to BoostCon. So my first BoostCon experience, I was totally lost. A lot of the stuff kind of made sense, some of it made no sense at all, and then the rest of it I was completely confused about. And so I wished that there was an introduction of some sort for myself before I arrived. And so that's really what I based this talk on. Some credits. So it just so happens that this presentation is almost the same name as this book. It's a great book. If you don't have this book, you should get it and put it in your library and read it. It has a lot of the ideas that we're talking about today, in fact almost all of them, and it's kind of the basis of a lot of things that happen in Boost and modern C++. If you don't have this book, you should get this one also. So those are two books that you should have in your library. And these slides will be available at the end of the session. All right, and then a couple personal credits here. For myself, Joel de Guzman and Boost Fusion were huge in my understanding and learning of how modern concepts work. Hartmut has spent enormous amount of time with me trying to make me understand things that I didn't understand. And then Baron, we're gonna steal a lot of his examples from his Boost geometry and the way his design is later on inside of this session, probably in the second half. And the reason is because it's a great example of how tag dispatching works. So we'll use that for our example of tag dispatching. And then Stephen Watanabe, if you are on the mailing list at all, he's always got incredibly great answers and is influential with the Boost Units library. And if you're not familiar with that library, again, another great example of modern C++ techniques. And we'll actually talk about that one at the very end too. So some of the examples come out of both the EPL book that I just mentioned and then out of the documentation here with the Boost Units. All right, let's get going here. We're going to start easy, and we're going to move along and keep building along the way. And let's start off with functors. So, easy, right? By this point, we all hopefully know what a functor is, but if not, a functor is a function object, or in other words, it's an object that we can treat as this callable thing. Why would we want to do that? What is a great reason to have a functor? Why would you want a callable object?
Callbacks.
Yeah, okay, callbacks. And why not just pass a function pointer?
State.
Okay, very good. State. I wish that thing was tilted.
They zoomed out in previous sessions somehow by doing something with a remote.
Sounds dangerous. We'll see when we get to a code. Oh, no, the code isn't good. We'll see. But state, yeah. State is the reason we want to use a functor, right? There's information that we want to store inside of some callback or some function, and then be able to access that later at the call site. We want to take and hold state in, and then send it out. All right, so there are slews of algorithms, right, that work on function objects. Yes?
So what's the, why shouldn't we use like a function with static variables versus, so in that case also we can store the state, right? So what's the benefit of having a function?
So we have an idea of why you might want to use a functor instead of a method with.
You can't pull that state back out.
Okay, you can't pull the state back out. That might be useful. What's another reason?
Multiple invocations
Yeah.
concurrently.
So multiple invocations. If you have a method that has static members in it, right? Static variables, local variables that are static, you're going to have a big problem with things like recursion. You're going to have a big problem with wanting to call this from multiple locations, right? So you want an object so it can store its own state. So state is very useful, right? We use state all the time. And it's great if we can wrap that up into an object and move it around. Okay, so how do we make an object callable?
Load the operator.
Okay, yeah, we overload the function call operator. So we take the function call operator and we give it the signature that we want to treat the object as a function later. So here, what is the signature of the function call operator? It takes an int and it returns an int. So at some point, I will have a functor, a function object, that I can treat like this callable thing that takes an int and returns an int. Now we're capturing state with this thing. How are we capturing our state? Okay, with the constructor, right. So we're going to pass state in at the constructor. We're going to store it within inside of our object, and then we can utilize it later when we access the functor. So here we create this mod.
This is now.
Now. Somebody have a credit card number I can use? This is an indicator that I never boot into Windows.
Okay.
All right, hopefully that doesn't come back again. That was annoying. All right, so we create this object. We're going to give it a name F. And we are constructing it with for. So for is going to be in its state, and then later I'm going to treat it like a function. I'm going to call F42, pass 42 in, and voila, it does what I want, right? I'm going to get modulus division, 42 divided by modulus, whatever it was, 4. And it's going to return then the result. So we use functors all the time in order to handle state. 2 days ago, we talked about something else that we could utilize for something like this, when we have small little function objects that we want to build in line. Lambdas. All right, great. So yeah, we get our output of 2. Everybody's happy. That's it. That's functors. Let's move on. But we learned yesterday that RAII does not stand with what we thought it should. It stands for something else. We have to ask John again later. I've forgotten already.
Responsibility.
Responsibility. Okay. We're going to use resource. Resource acquisition is initialization. So we hear this a lot, RAII. And it ends up that it's really important and useful. And it ends up that it's missing in a lot of code that I see in code bases, which results in some very interesting behavior at times, and one of which we'll look at here in a slide in just a minute. But it's needed in order to do exceptions properly. If you don't utilize it, it's very likely your code is not exception safe. And we happen to have 3 hours, very good 3 hours yesterday on this, and so we're not going to cover that in great detail, but we're going to talk quickly about a couple places where we see it. For example, in the Boost library, right? We have a mutex. We want to lock that mutex, but irregardless of what happens inside of our function, we want to make sure that that lock gets unlocked when we leave. So here we're going to go ahead and create a scoped lock object passing in the mutex. And on the constructor, it'll lock the mutex. And on the destructor, it will unlock it. So irregardless if something throws in here, if bar throws, I'm not going to end up in this wacky state where I have a mutex that's locked, right? That would be bad. So, amazingly bad function. This is a shorter version of amazingly bad function that I found in a code review for a client 3 weeks ago. You're pretty much guaranteed that you have an amazingly bad function if somewhere towards the bottom it has object.release. Or anywhere. Object.release, that's almost like an indicator right away that something bad is in there. So we have this amazingly bad function. We have a special resource, we're going to get it. We're going to do something here. Special resource update, some call, and then we're going to release it. What happens if some call throws? Yeah, the resource is not going to get released. Your very first exercise, quickly write a wrapper that will do the right thing. You'll know when we're in exercises because it says exercise. So, this is where the compilers get whirling, the keyboards get typing, it's the warm-up. What I want you to do is write some type of object that will use RAII and help solve this problem. You just got done reviewing this code. Just so happened the guy who wrote it isn't there anymore. Now your job to take it over and fix it. How are you going to fix it? Nice shirt.
Thank you.
I'll guarantee you that these 2 sessions will be a lot more enjoyable if you have a keyboard in front of you. Or at least sitting next to somebody who does. We had the social pic last night, we're all friends now. We'll just work on some extreme programming. Okay, how are we doing? Most people have an idea of where they want to go with it, at least? Okay. All right, this was, I put myself through the same test, you know, I try to think of the idea and then quickly write something. And so, it also means that probably there are errors in it. So this was my attempt at solving this problem. So I'm going to call it a better function. Better function is going to instantiate this helper, giving it a type, and which happened to be the type of my special resource. It's creating this local variable called block, and then doing the call that I had before. So it's a little simpler down here. I'm not doing my get and my release. So up here, what I've done is I've decided that get and release seems to be the common terminology that a lot of things like this use. And so maybe I can make a helper that can just be used for anything that has a get and a release. And so that's type T. And on the construction, I call get, and on the destructor, I call release. Make sense? So now if some call throws, it's okay because at least the resource will be released. And if I exit properly out of the scope, it'll destroy the lock and it'll be released also. Anybody have any idea what this thing is? This boost non-copyable?
Makes your counter constructor and assignment operator private.
Right, yeah, so I'd prefer not to have these things copied around. And so I just kind of stuck that in there.
RAII and copying don't mix very well. Moving is a different story, but
Right.
in C++ 03, you kind of have to learn this rule of thumb.
Right, and as you can imagine, the very first version of this that I wrote, which happened to be last night, I didn't have non-copyable. And then when the slide generated, the first thing I saw was, oh my goodness, that's really bad. So yeah, you don't want to copy around RAII objects. That kind of defeats the purpose. All right, make sense? All right, let's move on. So we have this thing now, this helper, but how do we talk about it? I'd really like other people to utilize my helper, right? Otherwise, everybody's going to just be making helpers. And so we call this, in general, we call them concepts. I need to understand, for a T, what are the different things that T has to support in order for me to be able to use it with my helper. And so there's got to be some way to talk about this, right? And so concepts will provide a set of requirements that have to be met by a type. Types that meet the requirements are said to model the requirement. So if I have a type, foo, and it had a get, and it had a release, then it would be a model of the concept that I need in order to use my helper. Concepts can extend their requirements. That's called refinement. And they're typically spelt with camel case. So if you're looking through like documentation, that's what all this stuff is. When you see camel case stuff, that's a concept. Requirements may include C++ expressions that must compile successfully, associated types that are related to the model. These are usually type defs. For example, iterator. Runtime characteristics of the objects that must always be true. Pre and post conditions. And complexity guarantees. So templates are really cool, but if we don't have a way to talk about what the requirements are on the types, then we can't communicate that to someone else. So let's take a look at an example of this forward iterator. And these are the different concepts that exist for the forward iterator. It can be default constructive. What does that mean? These are the valid expressions. It can be copy constructive. Accepts equality, inequality comparisons. Dereferenced when not null. Incremented when not null. These expressions have to be able to compile and be valid. Does that make sense? That's how we would describe a forward iterator. So a bidirectional iterator is a refinement on a forward iterator. So we refine it by changing a few things, right? So before, we had this. It can be incremented. Now we've refined it. It can also be decremented when not null. Right. Make sense? Those are concepts. We don't want to fall asleep, so we're going to start doing coding in here soon. All right, let's talk about policy classes. If you were in the Lambda talk, we had this as a policy. We had this fill method, and fill took a vector by reference, and some type that we call done. And while we were in this loop, we were checking to see whether we were done or not. And if we weren't done, we were just going to push back I and then increment I. And when we called fill, we created this lambda expression, became an object that was this done object. And what does it do for us? It looks at stuff.size, and is stuff.size greater than or equal to 8. So this is the idea of a policy, right? We're able to pass something in and have it do things. But this is at runtime. And modern C++ techniques are a lot about figuring out how to do things in compile time. So let's do it in compile time, or something. So a policy class is a template parameter that specializes behavior, and it's selected at compile time. Basic string. You all know what basic string is, right? It's this type def in here. Alloc is a policy. It has a default behavior for us. How many people set alloc on a string ever? Wow. Not even for fun? Yeah, we just don't mess with them most of the time, right? The policy that's there by default, it's good enough. But it's a policy that's going to describe to the string, to the internals of the string, how to manage memory. Where does it get it from? What does it do with it? That might be a behavior you want to modify, not necessarily for a string, but maybe for some other things, who knows? When we want to be able to modify behaviors like that, we set them up inside of a policy class. So let's go ahead and take an example. Maybe not a very good example, but an example. We have a pointer wrapper. And pointer wrapper is going to have a couple different template types. It's going to have this thing called T. It's going to have this thing called checking policy that has a default of no checking. Bad pointer policy that has a default of bad pointer do nothing. I can construct these pointer wrappers. If I default construct one, then I'm going to store a null internally. Otherwise, I'm going to go ahead and store the pointer how I'm constructing it. And what I'm wanting to do with my wrapper is provide different behaviors that I'm going to set up at compile time of what I want it to do if it encounters a null. So I'm going to overload my operator. And because I don't want it to have the same behavior all the time, and I want to be able to select it at compile time, I'm going to use these policies. The checking policy. Check the pointer. If it comes back as not for the pointer, whatever that means, then return bad pointer policy, handle a bad pointer. Otherwise, just return the value. Okay, we don't know what this thing's going to do yet, right? But we know that we could use this wrapper to wrap a pointer, and then we can give it some behavior later. The first set of behavior is how to check the pointer whether it's valid or not. The second part of the behavior is what to do if it's not. So how to check and what to do if it's not. All right. Just taking a look at this for a moment, what can you tell me about check pointer and that method as far as it's concerned with the checking policy? Is there anything that stands out? It's probably static, yeah. It's going to have to be static, right? Now, what do we know about static methods? What types of things do we know about?
Don't need an object.
Don't need an object, okay. And so since I don't need an object, it doesn't have to be instantiated, that means
Known at compile?
there's, pardon me?
Known at compile time, or?
It's known at compile time. Right, which is exactly what I want, right? I want this thing to be known at compile time. So let's look at my no checking policy. My no checking policy is very simple. It's static, it returns a bool. It takes whatever it is, it doesn't care, and it always results in true. All right, so now all of us, let's put on our compiler hats. We're compilers for a moment. If I am a smart compiler, or even probably a relatively dumb compiler, and this evaluates to true,
Get rid of that whole if and just return value.
I can get rid of the whole if and just return value. Exactly. So the compiler can just get rid of all this. And if the compiler already knows it's just returning value, it's probably a little smarter even than that, right? So by utilizing mechanisms that allow us to select items at compile time, the compiler can be really smart and take care of things for us. So we can write lots of code to give us lots of opportunities to do different things, but compilers are really smart and they'll figure out what to do if we can give them enough visibility of what's going to happen. So at compile time, we want to give them as much visibility as possible. All right, so far we're okay, right? Make sense? All right, null checking. So my null checking version looks exactly the same, right? It's got the check pointer. It's going to take t star, static and bool, but this time it's going to return p not equal to 0. So it's actually going to have to check something. All right, let's look at bad pointer. Bad pointer do nothing. Handle the bad pointer. What is it going to do? It's going to print out that my pointer is moldy, and then it's going to return my pointer, unmodified. So if I get here, check pointer, and indeed it comes back, it's null, because I was using my policy that allowed it to check, and I do bad pointer policy, handle bad pointer, and I pass it in, then I should get pointer is moldy and return something like null. All right, so let's do that. Let's wrap an int, new that int off, assign it 42, and then dereference it and print it out. Let's do the same thing, but we forgot to new it off here. And we get your number's 42 and a segmentation fault. So 42, and then at this point here, we're seg faulting. Now why are we seg faulting instead of printing out that my pointer's moldy?
So the checking policy. There's no checking policy, or it's no check.
Right, very good. So here I have taken and created this pointer wrapper with the default policies. The default policy was no checking. And luckily enough, I got a seg fault. Okay, so let's change this to not that. And say that we want now null checking. So we're going to create our pointer wrapper, and it's still going to be of an int, but this time we're going to give it a policy. We don't want the default policy, we want null checking as the policy. The rest of it looks exactly the same, and so now what we get is your number's 42 for the first part, my pointer is moldy, and still get my segmentation fault because all I did with my policy was return the value. Right? So I'm still dereferencing my null here. But at least I know that it's moldy. Okay, so the keys to policy classes are that they're static, right? They have static methods so that the compiler can figure out what to do at runtime. Excuse me, at compile time. All right, does that make sense? We're okay with that? Yeah. All right, let's move on. CRTP. Okay, curiously recurring template pattern. Every time you use something and you use it in such a way that you have your derived struct or class, and when you derive from the base, one of the template arguments is your struct, the derive, you're using this. And you might be using it for a couple different reasons. The first is static polymorphism. So what does that mean? What's polymorphism, first of all? just in general, polymorphism. I'll have to open the door and pull it off.
Selecting the correct type at runtime.
Selecting the correct type.
Delegating to a correct object at runtime.
Okay, getting to the correct object at runtime. Okay. So if it's runtime, absolutely. So in this case, we want to try to do it statically. What is the runtime overhead of polymorphism? These tables. Okay, so we have both resources in memory that are being utilized. We have a jump table that we have to go and take care of. We've got some things that aren't necessarily attractive, and potentially even more important, it doesn't necessarily always model what we really have in life. It may not really be runtime polymorphic. You may never have a pointer to the base class that you're using and trying to use in such a way. You're trying to extract behavior and utilize that same behavior through inheritance. The other thing you might be trying to do is inject behavior. Now, I personally think these are two different things, and we'll see why at least Michael thinks they're different things, but you might be trying to inject behavior into derived. So let's take a look. I actually hate this slide, so we won't stay on it long. This is what it looks like inside, right? We have some base that has an interface. We've derived from base and we passed it our type. We have an implementation at this level. Interface then calls the implementation by first casting derived type, casting this to the derived type. So here, this is a pointer, right? And it's a pointer of whatever the derived type is. And it's casting it using static cast to that derived pointer type. And then it's invoking implementation. So in the base class, even though it has no idea really what's going on, it's able to go ahead and cast to the right type, call the method it needs, and now the derived type's implementation is going to get called. So this is the basic pattern. Let's look at a different example though.
So this can be inline, right?
Yes, absolutely. Yeah, so the big win is, and this over and over again, modern C++ type techniques take advantage of showing as much as possible to the compiler so it can optimize things for us. If it knows what's there, it's going to do the right thing. If we hide that, it won't know. We're gonna see that later where things are going to get really convoluted, but compile down to nothing. All right, let's look at something called clonable. You ever have the need to have to clone something? Get that thing out as whatever the type? It'd be nice if you could just inherit from something called clonable, right? So what does clonable do? So clonable, because we're using CRTP, it's going to want to know the derived type. When I call clone, I want to get a new derived type back. So a pointer to a new derived type back, whatever that happens to be. But clone's pretty simple, right? What we're going to do is new one of these derived types off, and we want to copy construct it. Cool. So we're going to new one off, and we're going to return that based upon the one that we already have. So here's this. We're going to dereference this. We're going to static cast it to the derived type, const reference. So if originally we had a foo, we now have this thing as a foo const reference. We're going to new off that foo and then return it. So here we have bar, inherits from clonable bar. It has an int, very exciting. I can create a bar. I can set its value to 42. I can call clone, and I'm going to get back now a bar star. My clone value is 42. So this does exactly what we want for a clone. And it does it in a generic way by using CRTP. So here we are using, in essence, static polymorphism, right? We're getting to the right derived type by casting this to the derived type. So we cast this to the derived type pointer, and then we can utilize it. Does that make sense?
Why static cast?
Because we know what it is.
Just because we know what it is.
Yeah, we don't want a dynamic anything. Yeah, I mean, this is static, right? We want the compiler to take care of everything for us. We're telling the compiler, I know what this thing is, man. All right. Who's used enabled shared from this? Good. All right, so enabled shared from this is really great. If you have handler, how many of you have used enabled shared from this? Also use the asynchronous IO library. Oh, some of you don't. Though. That's interesting. Okay. Commonly, if you're doing something and you need to manage your lifetime of your objects in such a way where you don't want them disappearing, but you don't know how to hold on to them for too long, you might use enabled shared from this, and it might end up getting, you might have a shared pointer to a handler type, and you might bind that somewhere and stick it somewhere. And after all of the funness happens and the bind method gets called, you just want it to destroy. So that would be a use case. There's all kinds of different use cases. But the key here is that enabled shared from this, it's injecting behavior for us. And the behavior looks like this, somewhat shortened, but this is the basic behavior of enabled shared from this. It's going to inject this shared from this method for us. Shared from this is going to return a shared pointer t. There's a const version of it also. Notice also what it's injected for us, this mutable weak pointer called weak this. Enabled shared from this is using the weak this. Notice what it's not using though. It's not using anything that was inside of our derived class. So it's purely injecting behavior, things that we want, without actually affecting our derived class, or without utilizing our derived class as methods or members within it. So we're getting new behavior. The new behavior is, there's this private thing down here, and we've got a couple new methods so that we can get a shared from this back out. All right, because you guys are falling asleep, we have to do an exercise. Using CRTP, write a base class that adds this method, float profit. And it's going to calculate profit by taking something called output, dividing it by input, multiplying it by 42. Output and input are members of the derived type. So, what are the concepts for this type? Concepts for the type are that it has to have members with names output and input. All right, so, make sense? The derived class will have two members, at least. Output and input. And via CTRP, the base class is going to go ahead and access those and perform this calculation. We can erase, go. Maybe not erase. furious typing going on. Totally understand.
The Sigmund, somehow it doesn't show up.
It's because you're running Sigma.
Yeah, Sigmund and the VI, no matter how I did it so many times.
Right, so how are people doing? Okay with this? Somebody want to tell me any of the characteristics of their base class?
Template,
Okay, it's a template.
it accepts the derived type as a template parameter.
All right, great.
And then it has to static cast the, this to subclass star
Okay,
for accessing the members of the subclass.
all right, so it has to cast it to the subclass before it can access the members. What else about that method? Anything else? There might not be.
It has to call into the base. Using the after static cast, you're going to call into the derived class.
Right.
Either two ways something. Either you delegate to another profit method, or you get the input and output, and then calculate it.
Yes, we have to get the input and the output because we don't know that there's another method.
Get input, get output. That's
So Nathaniel, you're using a pointer?
Yes.
Yep. Okay. All right. This was my version of it. I ended up doing this just to make this prettier, right? So I created this thing called department, enable profit of department. And so now, after enabling this, hopefully I should be able to call profit on department types, on objects of department type. It has an output and an input. Profit. Here I have static cast my derived. Static cast dereference this to derived const ref. And now I have this derived, and I can now do return 42 times derived output divided by the derived input.
It's a good idea if you're doing this to get in the habit of using static cast, even if what you've got is polymorphic base class.
Yeah.
Because I at one point was using dynamic cast, and I used this tactic in constructor of the base class.
Probably not a great idea, huh?
It wasn't yet, and it's a derived class.
Yeah, you should just use static cast. Absolutely. Right, does this make sense? Yeah.
It's probably orthogonal to what you're trying to show, but you should cast formulas to float so you're getting integer truncation.
It is somewhat orthogonal, but we'll be getting there later.
And you could make profit const.
And profit could be const. Why would I maybe want to make profit const?
To show that you don't want to manipulate any of the instances.
Right.
when you call
Because
it.
I don't, there's nothing being manipulated. Now for this, it doesn't matter, right? But let's say if what was happening here is derived we were calling into derived different methods. If our method is really const, we won't be able to call into the derived types that aren't const.
Right.
And that would be a problem, right? So if it is const, especially in CRTP, right, you really want to make sure you're using that correctly, where it needs to be. You're right, that was also orthogonal to show, but great.
But just to point out, that's exactly what I did. I maybe didn't read it well enough, but I made my input-output methods. So if I had made
Yeah.
it const, it wouldn't have worked. So
Yes, yeah. All right, let's move on to type traits. type traits allow us to query characteristics about a type. Often, it's important that we know something about that type. And it just so happens that template specialization is nothing more than pattern matching. If you were in Bartos's talk, somehow I'm supposed to put a Haskell slide up here next, I think, and show how easy it is. But I'll skip that, because I don't even know Haskell. What types of things might you want to know about a type? What things might you want to know about a type?
Size of storage, storage,
Storage characteristics of some sort? Which,
Can it be iterated? Can it be iterated?
can it be iterated?
Yeah.
Okay.
Whether it's a pod or not.
Whether it's a pod or not?
I mean, it's a way of specifying policy for something that might in fact be a built-in type.
Yeah.
You know, when you have when you're taking an argument that is a user-defined class, you can just say this, it has to have a method that does the right thing, and I'll call that method. When the argument might be an int, might be a float, might be complex,
Right.
you don't have a place to specify that method, and so the type trait gives you an opportunity to say, okay, this is what you have to do.
Yeah. Okay, so we're building here, right? But one issue with writing generic programs in just any generic program is at some point generic starts falling apart. Not everything that comes in as a type T is going to support everything that you need it to. Or perhaps there's a performance improvement if you utilize it differently. How many have run into this where you end up having for this set of types one behavior, and for the other set of types another behavior. So you have two behaviors that can be divided. So you have two different types of T, right? Two characteristics of T. Yeah.
Well, I mean, standard distance.
Standard distance. Don't jump ahead. Standard distance is a perfect one, though. Why is standard distance a perfect example of what we're talking about?
Because some iterators you can do that like for a vector you can do that by just doing math.
Yeah.
Other things you actually it's O1, and other things you actually have to step through and it's O that.
Okay, and we wouldn't want to step through everything if we had to, or if we didn't have to, right?
Yeah.
So we'd like to be able to make determinations of what we have. And then based upon what we have, then do the right thing, right? Okay, type traits, that's what we're going to utilize to do this. Type traits aren't anything magic. Here's one that's going to tell us whether or not we have an int. So, struct is int. We have template parameter T, and within here we have static const bool value, and we just set it to false. We're going to then specialize T on the thing that we're interested in. In this case, an int. So we're specializing with the int, and now we can set value to true. So anything else that we throw at this is going to take this version of it, and we're going to get false. But if it's an int, the compiler will match it here, and we're going to get true. Does this happen at runtime, or does this happen at compile time? Right, at compile time. Again, modern C++, right? We try to get as much as possible done during compilation.
Is the same impacting the order of competitions?
No, we have to first
Define the generic one.
right, define the generic, and then we can specialize. So now, if we go ahead and say is int, give it a float type, an int type, and a var type, then we end up with floats aren't, ints are, and vars aren't. What would happen if I type def a var to an int to a var? True, right. It's just an alias, right? Okay, does this make sense? All right, let's think about, we want to compare if two things are the same or not. So I have two types, and I'm trying to make a determination in my generic code. are the two types that I have the same type? And if they are, then I want to behave a certain way. And if they're not, I'm going to behave differently. So, is same, type 1 and a type 2, and that'll be false. The specialization of this is instead of a type 1 and a type 2, they're both T. Then our static bool is true. And so if I have is same int and a bar, I'll get my 0, and if I have 2 bars, then they're the same. Is int the same as constant?
No.
No. Yeah, wow. Okay, so is int the same as const ref?
No.
Int? I hope not, right? Is a ref to an int the same as a const ref int? No. All right. So now what are we doing? Well, if we want to know, is this like basically an int, what would we have to do?
Is remove constant ref.
Yeah, we'd have to somehow erase the const ref part before we start making these comparisons. And we're actually not going to talk about that. It's called type erasure. And you can look it up. It becomes ugly really fast, as you're pointing out, right? Or can be.
But you don't have to do it by hand because there's a Boost library that removes those for you.
Exactly. There is a Boost library that already does it for you. And at least one of the authors was in a previous slide. We refer to Stephen on IRC very humbly as Obi Watanabe. And as far as I can tell, the man just knows everything. So. But yeah, there's already a great library for this. And so look up type erasure so you don't drive yourself nuts. Good question. All right. There's this thing called boost type traits, and then if you are lucky enough to work in a world where you get to use C++11, there are type traits there too. So we just had a couple here, right? Is same, is int. As you can imagine, there are all kinds of type traits that you might care about. Is base of. Now I'm forgetting all kinds of different things that I might have wanted to compare things against. Is this an integer type value, or is it a floating type value? There are all kinds of decisions that you may want to make about types along the way, and likely somebody in Boost or now in the standard has already done this for you, and you don't have to. But occasionally, you're not so lucky, and so exercise. Write a type trait that will be true if the type is a Boost shared pointer. Because back in October I needed this. Anybody running into issues with the fact that shared pointer is a templated thing itself? Okay, keep in mind that specialization is a lot like pattern matching. If you think about it that way, it's a lot easier. Trying to match patterns. Tell me you're still awake, it's okay.
Not bad.
You're right.
Now the Bitcoin is the only on my hand, but I type it in the notepad.
No, but I'm impressed that you're sitting there coding with your phone. And I'm not sure I've ever seen anybody actually really try to do that. Not for more than a few seconds at least.
You really need different keyboard layout.
Yeah, definitely.
But it's honestly not as bad as I thought it would be.
Really?
I've just given out of like capitalized things and should be capitalized.
Remember, we're supposed to shut these things off. Right, how's it going? How many of you have a solution? Right? Okay. Let's at least see what I did. Oh, let's not see what I did yet. Let's ask what other people did, because that's always more interesting. Who wants to divulge their very secret code?
I have a specialization which also is a template which takes a T.
Okay.
And then struct is boost share pointer, which templated takes a boost share pointer of T,
Okay.
which returns a T, which is a specialization.
Okay, one that just was T and was false.
Yeah.
All right. Sound good?
Yeah, the rest is which more generic case just takes a T and substitutes.
All right. All right, so, you know, if this was your first time doing this, my suspicion is this hung you up right here, was that you could stick the T right in here, not worry about the fact that you don't have to worry about all the T's that are ever going to exist. Now, if I was interested in that, right, if I wanted to know, is this a boost share pointer to foos, then I could do that. I could specialize in, this would be foo, and there would be no typing T here at all. All right, does that make sense? All right. We're moving slightly faster than I thought we
I
would.
get the answer is true, but if instead of put share in the real world use a derivative class, share pointers should have something too. Right?
If you used what?
Yes, imagine you extend share pointer to something else,
Mhm.
and then you get the struct is share pointer with the derivative class.
So you have extended share pointer to your own type?
Yes, let's imagine that were the case. So it's still true in the derivative class.
But, so what do you guys think? So he has no longer a shared pointer, but he has foo that has extended shared pointer, so
Shared pointer.
foo inherited shared pointer.
Sometimes you have a base class. Later you make, derivations of the
Right.
base class, but you still want to know if it belongs to the family.
So is this going to return true then if this is a foo instead and I'm matching it against shared pointer T?
Yes.
We got a yes.
If it's publicly derived.
If there's nothing more specialized that wants it.
Okay. So all you have to do is you just have to ask questions in such a way with this look on your face and you sort of question them. What is it that we can't do easily? What if this was foo? and I passed in a shared pointer. Yeah, now that's false, right? But what if I wanted to know if instead of things based upon the base, but that the other stuff around? Does that make sense? What would you do?
Then you probably should make a type trait that says is derived.
That's almost right. You should go look inside the type trait library. Because it's probably already there.
Yes.
It is. Correct. It is there. Okay, so this was the part of the talk where we got to make the decision on which slide we went next. And we're not going to go to the one that's very nice. Hopefully all this selection fancy stuff works. Look at that. All right, we'll come back to tag dispatching in a moment because that's going to take more time than the rest of this first half. Oh my goodness.
But it's not an error.
It is not an error. So if you fix something in your Beamer slides, remember to regenerate twice so that the indexes get updated. All right, it's still right there. Substitution failure is not an error. So we talked a little bit about this yesterday, just briefly. What does it mean though? Substitution failure is not an error means what?
Was the wrong type which doesn't support your policies. You want to know.
Say that again?
If you try to instantiate one type which you are not expecting for a particular type,
Okay.
then you want to know that compile time.
No, you don't want. You don't want to know it.
You don't want to throw it. You want to keep going.
Yeah, there's infinitely number of things that you could probably pass and the compiler would give you errors about, which would make templates completely useless, right? We don't want it to do that. But think about the thing that we had previously. If we're trying to match a simple isInt, and one of those specializations, right, is an int, but it's trying to compare this thing it has against a float, and it says, oh man, look, there's this thing that should take an int, it's been specialized, but you got a float, there's an error here. That would be really annoying, right? So by default, the compiler just can't do that. It would be a completely useless compiler. So that just makes sense. But what has happened is people figured out ways of abusing that behavior to do other things instead. So now, let's abuse it this way first. Let's not. Let's continue to talk just for a moment. So just a moment ago, we were talking about type traits, right? And it's interesting to know whether a type is of something or not. Maybe it's interesting to know whether or not this thing is an int that I have, because there's something very special I do with ints than I do with everything else. Well, we now have a type trait that tells us that, but we don't have anything else yet, right? We know whether it is or not, but now what do we do with it? We want the compiler now, we want to write code so we can make a selection based upon it being an int. We haven't gotten that far yet. So that's what we're going to talk about here. This is a fairly real example of a problem that I had where I have this thing. It's a functor make instance where it's given a type, and later the functor will be called, given some configuration, and it'll get the thing back. But it just so happened that some of these types in the system were of just nice, plain friendly types, and then some developer decided he didn't like it that way, and he wanted all his types to be wrapped in shared pointers. And this broke in dramatic ways. It was spectacular. Because it was doing stuff to pointers that it shouldn't be doing. So I needed to figure out, do I have something that's actually a shared pointer? Because I'm going to have to act differently if I have a bar that's wrapped in a shared pointer versus just a bar. Those aren't the same things. I'm going to have to do something else. So, this is what I did. I said, okay, I have my functor, this make instance thing, and one of its template types, as we saw earlier, was the type that I want to return, the instance type. So here on this slide, instance type of foo t, and here we have an instance type that is actually the shared bar t, which is a shared pointer of bar. And I'm going to add another parameter. We'll see why we want to add the other parameter in just a moment. But here my function operator is going to take whatever this special value thing is, some configuration information. It's going to make one of these types. It's going to do something that we're going to see in the second half of this, called tag dispatching based upon the type, in order to do something special with my type and the configuration. Somehow it's going to apply this fill adapted stuff inside there. I don't know what it's going to do, some special work. And then it's going to return it. So you can imagine all kinds of things that might go wrong if my instance type was actually a shared pointer in this code, right? It's not too hard to think about. Now, this here means what? Shared enabled equal void. What is that thing? Just a defaulted template parameter. And so if I don't provide a template parameter, if I don't provide a templated type when I create these make instance functors, what is it going to be? It's going to be void. So if I don't give one, it's going to be void. So ignore the man behind the curtain, which is this top part for a moment, and let's just look at the bottom for a quick second. I now have an instance type that is one of these boost shared pointer things. So I have to create them differently. I need to new one off. Just so happens that shared pointer lets me look inside to see what the element type is. So I can say, and what is this thing called? This element type. We talked about these concepts early on, right?
What type?
So now, why do I have this type name here?
Because it doesn't know if that's a function or if it's a type def or if it's a type. Because
Why doesn't it know?
it's a dependent type, so
It's a dependent type, right? So it's a dependent type. We're telling the compiler, look, this is going to be a type eventually. Right now, we don't know what it is, but eventually this is going to be a type. So if I had shared pointers of bar, this type would become bar, right? So I'm going to new a bar off. And then instead of my cute function I had before, where I was passing in just the instance that I had, I'm going to actually need to pass it in differently. It's receiving it by reference on the other side. So I'm going to dereference this thing because just passing it in as the shared pointer caused grief. And then I'm going to return it. So this is why I had to do it. Now how am I going to make that selection? Well, we had that defaulted version earlier, this thing, shared enable void. But now instead, I'm going to use this thing called enable if. And this looks a lot like that type trait we had earlier. So if the instance type is a shared pointer, this will be what?
It'll be an instance of or its type is shared pointer. Or value in some place.
Yeah. Might have been an idea. How else could this work? That's the problem. They didn't have my code here, did they?
well, the boosty way would be for this is shared pointer inst type if it's a shared pointer derived from like true type.
Right, from true type. So it could be that the type is considered a true. So before we've been putting this value inside, right, a static value and looking at it, bool true, bool false. But it could be that is shared pointer, when it is a shared pointer, is a type that is a true type. And towards the very end of the second half, we'll talk about some of the MPL types, how we would do that. The end result is this is going to be this true type, so that my enable if is true when I have shared pointer things, and it's false all the other times. Now, to get this thing to kick in, notice I don't need to give it the second parameter. I don't have to give it the other templated type, because it's making it on its own because it gets instance type, right? So it's specialized here. This version defaults to void. What does this version then become if it's shared pointer? Was that a hand? A flip of the hand, yeah.
It's void.
What's that?
Void.
Void?
Yeah, I think it's the default implementation in enable div.
Okay.
If you're asking if it is a shared pointer?
Yeah, then type exists.
Then type exists. So I'm going to use this enable if to allow me to take my type traits and to make decisions then at compile time which one I want to use. Again, that's the key, right? It's at compile time that I'm making this decision, not at runtime. I don't have to worry about at runtime making choices, but at compile time the choice is going to be made. And again, if we can make more and more visible to the compiler at compile time, it's going to do better things for us. It's going to optimize in ways that are really cool. Now, I believe we have. No, we don't. Never mind. We'll do another example. Okay, so this is from the JSON library that we'll be releasing next month. And this snippet of code is compliments of Jeroen, who is at the conference and in some other building at the moment, and is speaking tomorrow about his course library. It ends up that sometimes on constructors, bad things happen when you have all kinds of constructor types that can, constructors that can take all kinds of different types, and you get conversions that you don't want. And it just so happens in JSON, we want to be able to distinguish between integers and floating point things. We need a way to do that, because we want to treat them differently. So here, this constructor is going to enable if cool type trait is floating point. So what would is floating point be true for? Float, what else? Double. So anything that would meet the requirement of what we would consider floating point types. So if it ends up becoming a floating point type, then this constructor is a valid choice that the compiler can make. It can make that choice. And then we're going to do something. We're actually going to, whatever this happens to do, right? This base type double T.
In a way, this is a better example than the previous one, because the previous one you could have just specialized with your pattern matching from the type trait in the class itself. But in this case, you're eliding a bunch of different specializations into that base floating point.
Yeah, good point. Thank you. And the other one ended up being one of those where it was appropriate for the original use, and then as I was taking more and more code out, it became not a great example. But yes, so do you understand what Dan is talking about? So here we're saying that is floating point. This is a bunch of different things that it can be enabled with, right? I don't have to write all these specializations. I don't have to write specialization for my float and my double. I can just write one is floating point. So anything that matches the concept.
May I add to the previous example, there was also the thing about this example is that you have function templates and you derive the type from the argument.
Right.
With a class template, you have to specify the argument as a template.
Right, yeah, thank you for pointing that out, because I clearly forgotten. That's why I have the two examples. So the previous example, we're specializing on a type. In this one, this is a method, a constructor, right? It's a method, and I want to disable one method and enable the other under certain circumstances. Or in essence, really, I really don't want this one to be around if it's not a floating point. And I really am not going to want this one to be around if it's not an int. That's kind of how it boils down. I want the compiler to even think about it. And so enable if allows me to do this for whole types, for methods. We'll look at the different, we probably don't have a slide for that. So we have to, it's either the return type, an argument that we end up adding, in essence, an extra argument. Do I need this argument in the constructor? I don't need it. I need it to help me specialize. So with the constructor, the rest of the constructors for this thing, they just take one value. This one's a little special because it needs to try to determine whether or not it's floating point or not. Now down here we're doing something even more complex and very cool. We're enable if, and then look at this thing, man. Boost NPL or. Enable if whatever t is an integer type, or it's an enumeration type. So what kinds of things could be integer types? All of those things. And it just so happens, though, that enumerations aren't, but I need to treat it like one at the moment. And so I've added it in. I want it to be enabled so that I can get that conversion. So I'm enabling it using this really cool Boost NPL thing, part of the metaprogramming library, and we'll see that at the end of this second half. So I'm passing here t, whatever the type is. T, is it an integer type? No, but it is an enum type, so it could be either of those. And then I do the right thing. So sometimes you have issues. How many people have these issues where you get conversions on constructors that you didn't necessarily want? You need to be able to distinguish between floating point types and int types, right? I mean, this happens all the time, right? This is the way to fix that. You really want one of them not to be around.
Yeah, it's problematic here that the top one is cast is forcing that float to a double. That doesn't round trip.
It is not problematic for what we are doing. But so those are the types of things you have to ask each time you use stuff, right?
I will really do that all the time. That this goes to the round trip.
No, it won't. All right, so my opinion about Sphena is, first, use it judiciously. Personally, I think it's hard to use. You have to create extra parameters in places that you don't naturally need them, argument. But when you need it, it's the only solution. Sometimes you have a choice. Sometimes you can implement the solution using tag dispatching or Sphena. And we'll look at tag dispatching in the second half. The other thing is, again, type traits. Learn about the existing type traits that exist, and then go read up on enable if. And as far as Sphena, that's all I want to talk about for enable if. The rest of it's just, we've taken another 3 hours, I guess.